So this video is a supplement to the teaching with parametric equations. Just there's a couple of notation, mainly just notation, but also kind of how parametric equations are used. So what you should understand at this point is, a parametric equation is when we have an equation, parametric equations are described using two different equations, where the one equation gives you the x coordinate, and another equation gives you the y coordinate. So, and usually the two equations are in terms of some other variable, otherwise known as a parameter. Like in this case, it's t. So we have x and y are the same x and y variables that you're used to, but each of those variables are a function of t. And now often this, of course, becomes very useful. Maybe one of the obvious uses for it is t is time. So often the x coordinate and the y coordinate are being affected by time. And so that's how this would be used, or one example of how it would be used. And at this point, you should be pretty fluent with that. But another way to write this notation-wise is in terms of vectors. And now I know that some of you have had more experience with vectors and some of you had less experience with vectors. But we can write a vector like this, where we'll have this is not a curved or this is not a parenthesis or one of these things or one of these things. It looks like a greater than or less than symbol. But what we have is something like this, where you have x comma y. So this is be considered a position vector, where x is describing the horizontal position and y is describing the vertical position. So you could write it also like this, that if we're referring this one up above, you could have t squared plus t here and 3t plus 4. And this is just another way to write this same type of, it's a notation for writing this same type of thing, another way to express this. And so this, you would think of this as, this is telling you the position horizontally, this is telling you the position vertically. Now the reason why one of the reasons I'm bringing this up is because if we refer to this as the position vector, let me do this. Then if we take the derivative of that, then that produces a velocity vector. Now, because we have varying levels of vector understanding, I'm not going to go real deep into this, but I just wanted to kind of scratch the surface so you could get the idea. So in this case, then this tells us the position of the horizontal position and the vertical position of whatever it is that's moving, and then this would refer to the horizontal velocity and the vertical velocity of whatever it is that this thing that's moving, this point that's moving. So you could write, so that would mean this right here would be the velocity vector of this specific one. Now, why is that useful? Because you could do all kinds of cool stuff with talking about the velocity of the particle and stuff like that. We're just going to get into, for example, I think I will ask you to find when is the particle not moving. And so the only way we would do that is we would know the particle is not moving when both the derivative of x with respect to t and the derivative of y with respect to t is 0. Because you could have x, they both have to be equal to 0. So, because you could have dx dt equal to 0, but then dy dt wouldn't, because it's, so in other words, a particle could be moving strictly horizontally, right? Or strictly vertically. So you can see in this situation, we could take 2t plus 1 and set it equal to 0. And that would give me 2t is equal to negative 1, which means t is equal to negative 1/2. So that would mean the only time that the particle is not moving in the horizontal direction would be when t equals negative 1/2. Now sometimes that would mean it would never be, because sometimes we'll describe a parametric equation over a certain interval of t's. So if the interval of t was from 0 to 25 or something like that, then that would mean that my particle is always moving in the horizontal direction. Now, when we look at the vertical direction, notice this 3, there's no way to make 3 equal to 0 because you're asking when can 3 be equal to 0? Of course, 3 is never equal to 0. So that means that this particle is always moving in the vertical direction. So, this would be an example. In this case, the particle is never stationary. It's moving all the time, because there's no way to make this equal to 0, and the only time this is equal to 0 is outside of the domain. Now, even if this is inside the domain, this still wouldn't mean the particle is not moving, because it's moving in the vertical direction even when it's not. So that would mean if the time equals -1/2, that means the particle is moving straight up, because it's not moving to the left or right at all, because at t equals -1/2, the velocity in the horizontal direction is 0. Okay, so this would be the horizontal velocity, and this would be the vertical velocity. Okay, so that's just a little snippet about position vectors and velocity vectors, another application of parametric equations. And so this will help you again get an idea of how these are used. And again, if everyone had a better vector background, we might go into this more deeply. In fact, this leads towards something you'll see in Calc 4 called vector valued functions, which are really cool and useful.